I'm not one of those scientists that gets to have a lot of fun. I'm not the person that they send to take selfies with penguins or make cocktails out of 500,000-year-old ice. They tricked me a long time ago with flattery and turned me into someone who creates numerical models of the ocean. And one of the reasons I love ocean modeling so much is that we can make really pretty pictures like this one here. That was created by it's our newest generation of ocean sea ice model in Australia, created here by the Consortium of Ocean and Sea Ice Modeling in Australia, which is a uniquely powerful community that we're very proud of. And just take a second here to look at the setup. Oh, geez, trouble already. Just to appreciate the setup, I think it's remarkable. We have this continent, Antarctic, covered in ice that equivalent of 60 meters of global sea level rise, is positioned pretty much smack dab on the South Pole. And it's surrounded by an immense body of water, the circumpolar Southern Ocean, that is actually filled with warm water, 3 to 5 degrees Celsius above the freezing point of the ice. And this warm water is sitting just off the continental shelf of Antarctica. So below this white blue sea ice that's fringing around, sitting all underneath that is this enormous body of relatively warm water. The sea ice in the winter, as it's shown here, covers about 50% of the Southern Ocean surface. And in the summer, it declines to about 5 to 10% of the Southern Ocean surface, making it one of the greatest seasonal changes on our planet. And the presence or absence of that ice completely dictates the air-sea interactions. The squirrely bits you see off the edge of the ice, showing the gradients in the surface currents. These are the things that the physical oceanographers get really excited about. The Southern Ocean is uniquely turbulent, and this turbulence plays a fundamental role in the dynamics of the Southern Ocean. It also takes an immense amount of computing power to simulate these fine-scale structures. And the amount of supercomputing power that we have in Australia to do simulations like this is declining. And we are losing our competitive advantage when it comes to supercomputing resources. Hidden within this network of turbulence is a network of currents that is key to the functioning of our global climate. The Southern Ocean, or our planet, Earth in general, this climate is functioning as a heat engine. Its goal is to move heat from the equator to the poles. And the Southern Ocean really is the beating heart of this heat engine. It's the place where nearly all of the ocean's old water, water that last touched the atmosphere before the Vikings started raiding Britain 1,000 years ago. Water that knows nothing of the Industrial Revolution. It rises up from the depths of the Southern Ocean to touch the atmosphere, to get introduced to our anthropogenic atmosphere for the first time. Of course, what goes up must come down. And so as part of this renewal process that's happening in the Southern Ocean, this old warm water rises up and is sent back down as new Antarctic bottom water. And this renewal process is really happening in 4 key, I was told to use the pointer. Yeah, it's only happening, this renewal it's not showing up.
The trackpad.
Trackpad on this thing? Yeah, it's not showing up on the big screen. That's okay. It's on the pretty picture. This renewal process of sending bottom water back down is only happening in a few key locations around the Antarctic continental shelf. Actually, quite small spots where this is actually occurring. And so overall, I think of the Southern Ocean really as our global ocean. It's connecting all of the other ocean basins together. It is the one ring to rule us all. Thank you for appreciating that. Thank you very much. It is this process of renewal in the Southern Ocean that makes it the key, the essence of our changing climate. Where is the heat and carbon that we are producing going? Well, about 40% of the carbon dioxide that we've emitted is being absorbed by the Southern Ocean. Greater than 90% of all the excess heat we're responsible for is being absorbed by the ocean, and 2/3 of that or nearly 60% of the total, is being absorbed by the Southern Ocean. That is roughly equivalent to the energy released by 7 Hiroshima bombs going off in the Southern Ocean every second for decades. And so the Southern Ocean is big. It's very big, but it's not so big that it can absorb the energy from 7 Hiroshima bombs per second without there being some implications. And so understanding how this Southern Ocean is going to move this heat and carbon around is the key to understanding our future planet. As there's clear signs of impact of changes in the Southern Ocean. Of course, one of the clearest is the changes in the Antarctic ice sheet. And you're going to see plots like this all day. Paul did a great job of describing it. The red blobs, mostly in West Antarctica, are where the ice sheets are rapidly melting, a few in East Antarctica as well. And it's clear from paleo evidence, if you look at past climates, that Antarctica can contribute many meters, several meters, even tens of meters to global sea level rise within a few centuries, okay, on that sort of time scale. And it is also very clear that these ice sheets are melting from the bottom. They're melting where they're coming into contact with warm ocean water. And again, just take a moment to appreciate how remarkable this setup is. And so it's just a schematic here of an ice tongue sticking out from Antarctica. These tongues are huge floating ice shelves. They can be hundreds. You think the Ron ice shelf is 800 kilometers long, sticking out over the ocean, and 800 kilometers wide. So immense ice shelves sitting on top of the ocean. And when they interact with warm water at their bottom, they melt. And as they melt, they're sitting on this reverse slope bed where the ground actually gets deeper as you drop away. And this is the physics of that are just terrifying in terms of runaway sea level rise. The thing that's wrong about this schematic is the little red blob. That's not a little red blob. It is pretty much almost all of the Southern Ocean is warm enough to cause problems. All the water above 4,000 meters deep, and it's sitting right on this continental shelf edge. They call it the continental slope. It's not the slope, it's a cliff. I'll show it in a moment. There's nothing slopey about it. It's a cliff edge. Yeah. So the key to understanding what's going to happen in Antarctica is understanding when and where and how much of this warm water that's just sitting there waiting for an opportunity to get onto the shelf. Okay? Of course, as the ice shelves melt, they put fresh water back into the ocean circulation. And that's that little blue line you're seeing there. And as we can rapidly melt these ice shelves, we are freshening the water on the continental shelf and in turn changing the Southern Ocean circulation. Oh, they played. Well done to the organizers. Thank you. Yes. What did I want to say about this? 1 second here. Yeah, as I said at the beginning, the Southern Ocean is a place of great renewal. It's where old water rises up to the surface and is sent back down as new Antarctic bottom water. And that's what's shown in this incredible movie. Again, this is our newest generation of ocean sea ice model in Australia. We are indeed the best in the world at simulating the Southern Ocean. We should all be very proud of that. And what you're looking at here is one of these locations where the dense shelf water, whoa, awesome. Where this dense shelf water is cascading off the continental shelf into the abyss. This is in the Ross Sea. These are essentially underwater waterfalls. This dense water is formed by air-sea interactions on the continental shelf and then cascades off an underwater waterfall to fill the abyssal ocean. Roughly 30% of the entire global ocean is filled with water made this way. These aren't average waterfalls. The largest waterfall on land is Angel Falls in Venezuela. It's 1,000 meters tall. These waterfalls are 2 to 3 kilometers tall, just underwater. And there's 5-8 million cubic meters of water pouring off those cliff edges every second. It's mind-boggling. Yeah. As the ice melts, and freshens the water on the shelf. The amount of this dense water that's coming off the shelf is decreasing, and the amount of bottom water that in this region of the Southern Ocean is declining rapidly. It's essentially deflating. It's dropped by about 30% in the last few decades, according to observations. And so if the Southern Ocean was a patient in the hospital, its pulse would be dropping, its oxygen levels would be dropping, and its heart rate would be dropping. On the bright side, what a movie. No. And thanks to funding like ACEAS and AAPP, we are coming up with profound new understandings of how the Southern Ocean works. For example, we now know that we can monitor the health of these overfalls from space. And I'll finish there. Thank you very much.